And we're off. Okay, so this is Travis again. Another video, another project, another day. Today it's actually looking good outside and nice clear weather, about 60 out. But besides that, the reason why I'm doing this, reason why I'm feeling awake, is because this video is going to be starting a new project of mine that I like to call the Match a Picture to a Database. And to describe that a little more, what I mean by database is like a bunch of images that have certain information to them, their number of pixels, like their dimensions, their width, their length, their the type of intensity per pixel, the average intensity per pixel, the um, the dominant color or things like that. And then there's also like noise that's associated with images, filters applied to the image, the original image, the geographic location of the image sometimes, and stuff like that. So that it has metadata. I think that it would be correctly used. And basically, what I'm doing is I'm taking an image. Say I have an image of a house in I don't know, New York or something, or even here in Northern Virginia. Take a house and you want to find out if it matches an image of this other house, this other image of a house, but you don't know if that image was taken the same place or was done by the same person, things like that. So the idea is that you go down to the very small grain, which would be the pixel. And in this case, what I'm going to do is I'm going to make a little, this is my Google Drive here on my other account, and let's create a document. Let's see, drawing. There you go. And we're going to call this. Let's just call this pseudocode. Pseudocode code for match. Not a MAC address. That's not a project. Match a picture to a database. Okay. So let's create a text box here, and then first variable. From my notes, now here I'm just gonna put it out there. These notes may seem like weird, or like you might not be familiar with some of the terms. They're either in some cases it's math terms that I haven't heard of myself. I'm still taking notes on that, reading, doing research, and then other parts. Um, they're digital image. They're pertinent to what's called a digital image, not just an image, but a digital image. So I'll explain that a little bit later. So first one is it's called intensity. Okay, so you have to look at the intensity of a pixel, and I have here saturation, right, and hue. Now hue. Uh, well, let's do a quick search here. Let's see. Define hue in image processing. There you go. In the image for time. Hue is one of the main properties of a color defined technically. Okay, so this looks alright. Looks safe. Defined technically as the degree to which a stimulus can be described as similar to or different from stimuli that are described as this RGB and Y, as programmers might look at it, and so on. Okay, so that's hue. Okay, and then computing hue, as you can see, uses math. Trigonometry here is clearly used to create hue from RGB and so on. Okay, so that's hue. So this is called HSI, and I have here this is the HSI info. Then here's the RGB value, which is in a column vector format. Now, what that means now in Matlab, this program or this app will most likely be utilizing Matlab syntax. And Matlab looks simple. It's mostly for matrix operations, and it also uses a lot of fancy math, well, depending upon what your program is demanding. In this case, this will be using advanced math. So now we move on and we find that noise, and this is not what you typically hear. It's not like what you hear noise. It's more of a descriptive noise. So to show you, there's something called Gaussian noise. So define Gaussian noise, for example, will tell you this: has a random and normal distribution of instantaneous amplitudes over time. So if it's instantaneous, that tells me it's probably going to be using math like trigonometry and stuff like that. Okay. Yeah, and picture below. Yeah. So let's look at that over time. Sample of Gaussian noise with normal bell curve. So this is bell curve. I don't know what that means, honestly. Yeah. So there's that. Okay. Now if you do Gaussian noise, you can see there's a lot of stuff here. A lot of math too. So then you look at this image, triple high definition noise reduction. So block noise, Gaussian noise, and mosquito noise. It's interesting. And then there's the clear image. Grainy image, mosaic-like artifacts, and flickery edge. Yeah, it's true. It's a type of, it's like a filter. I think that's kind of what it has to do about. So there's a Gaussian. Okay, and then in parentheses, put in Gaussian. Question mark, just in case there's other types, because there are other types of the stuff, other types of noise. And there's location, so the geotag. And I said check by using, I didn't finish this note actually, but this says check by using, and I'm gonna finish it and say check by using geographic location. Okay. Location, and then Laplace. And now this is where the math comes into play. So Laplace transformation, and I wasn't sure about this if that's the correct term, but I will tell you now it is after reading a little more. And then there's also Fourier series, Fourier, I think as Mr. Williger said. Series might be pertinent. Taylor series is another one. Let's create a little dash line. Oh, better idea. So these are the coming out right now. These are new notes. So this would include Taylor series possibly. For just straight up series, it's expanding on multiple sums and terms and stuff like that. And then there's also Lagrange. Algorithms. Let's put that one, algorithms. And let's see, there's what else is there? There's a lot of stuff here. Lagrange, yeah, it knows what I mean. And then Lagrange, and I'm trying to think. That sounds about right. Sounds about right. Okay, so there's that. So there's that set of notes. Now let's find my other set of notes. I think I have some more, and it looks like I do. So this is where the actual pseudocode comes into play. So this pseudocode is something that can be applied to any programming language you ever use. It's meant to be universal, like in a sense. And by universal, I mean like it goes to anything, anywhere, and applies everywhere and anywhere. So let's see. Match picture to a database. So in some languages, var is the syntax, like JavaScript. This is how you do it. You say var and then the name of the variable. My first variable I said is intensity, and you can. This is my way of doing it. 6. Okay. Pix saturation. Okay. Pix hue. So this is all of your. So this is your HSI, pixel HSI info. Pixel HSI info. Now, since I'm using Matlab, it's going to be very interesting because I haven't really done a lot. I've really just learned from my sister when I helped her out with things here and there. So yeah, then okay, so here comes a little bit more interesting, a little more well, at least to me. So this is your RGB value, or value set, and this is going to be a column vector. Now, column vector, um, column vector. There you go. Oh, extra L right there. So let me show you I believe, if I remember correctly, this is a Matlab editor. So I like this. This guy is pretty good. So you can do x equals 5, semicolon, right? And that doesn't do anything. Now in MATLAB, if you do x equals 5, you don't do a semicolon, it returns what you just put back in. Now this is an editor, so keep in mind, it's an editor, it's not a compiler, not an interpreter, not any of that. It's simply an editor, so it might not have certain functions. And you can create your own functions. I still have yet to learn that. So there's that. And if you wanted to create a variable type, I think you can do strings and characters. I'm gonna say hi. Let's see how that looks. Y equals hi. Yeah. So then let's see. Maybe y dot length. Y dot length. Yeah, so it doesn't look like it can compute the length of that string. I'll find out how to do that later on. And so that's how that looks. So then say we want to do a little bit more. MATLAB is matrix, okay? MATLAB is matrix labs or stuff like that. So let's create a more pertinent example. Say you want a array, right? And you just want x is equals I think it's 1 to 5. I think that's the syntax. There you go. So that's matrix in MATLAB. Who knew, right? So then let's modify it. Let's say z actually equals 1, increase for every other one, and end at 5. That's what that means. Start, end, how much you want to increase it by every time. You get 1, 3, and 5. Now that's pretty nice, right? Here's the trick though. If you instead want a column vector, which is what I'm using for RGB, this is what you're really going to do. You're going to say RGB equals, oh, that's interesting. RGB has a highlight color. Okay, well, we'll ignore that. We'll say var RGB. RGB. Okay. So for RGB equals, what do we want to do? We want to make a column vector. So, if I remember correctly, the way to do that is you go, let's say it's 1 to 100, right? 1 to 100, and let's do it. 1 increase 10 to 100, and then let's put 8. I believe that's how you do it. And there you have it. This is a column vector. It has one column and a bunch of rows, and each row has exactly one element. Element 2, element 3, and so on. And I don't have much time left, so I'm gonna hurry up here. And so we got all this, and that's RGB. Then geotag. This is how you'd store your location of where the photo was taken, stuff like that. Image height. Image height, image width, and then what else? Noise type. So this is going to be like what noise you're applying, what filter. Okay, so pixel. This is the key. This is the key. And we're slowly running out of time. And then this is average intensity. This is also an important variable. And then yeah, okay. And I will do another video in just a couple seconds, and I hope you don't mind. Bye.